Hello friends! Today's video is the first of a series of videos in which I will show you how you can build your own lab power supply. And because it's one of the key ideas of my channel, I will show you how you can salvage a lot of the parts required. In this video I will show you how I built a basic lab power supply based on an old audio amplifier plus two commercial switching converters. In the next episode I will then show you how I add a self-made linear regulator to this device, and then I'm planning to show you the work on a second unit that is based on an old AV receiver, and that build involves, among other things, the planning and construction of two self-made buck converters. And I know that some people in the audience might be skeptical about quote-unquote destroying audio equipment like this. And believe it or not, I'm actually someone who is very much into audio equipment. I have repaired and restored more classic amplifiers and receivers than probably most people in the audience. And here are some examples of my work. This is a Braun CSV 500 from 1969, of which I have repaired and restored several units over the years. And here we have a 1974 Braun CEV or Regie 510, of which I have also repaired and restored numerous units. And these are the kind of classic audio devices I would never destroy, and I can understand that people feel sensitive about that. But the devices that I'm going to use in these videos here can be bought for very little money here in Germany, and in comparison to the Braun devices, they really are not collectibles. And I hope that I will be able to show you over the course of these next episodes that these kinds of devices, especially if they are broken, can be purchased for very little money these days, and that they, on the other side, offer a lot of the components needed for a basic lab power supply. So the first thing, how do you get your hands on one of these? At least in Germany you can just go on eBay Kleinanzeigen, that means eBay small ads, and that's a platform where people typically offer things for fixed prices. And here you can find a whole range of AV receivers for prices around 10 to 25 euros. And if there is a VB behind the price, that means that you can also bargain for a lower price. And the Sony amp that I'm using in this video has a broken power stage, and I got it for 10 euros. Okay, so let's start today's episode by taking a closer look at this audio amp. It's a Sony brand LBT V702. And as far as I know, back at the end of the 90s, this amplifier was sold as a standalone component that belonged to a three-piece audio system with a radio receiver, a CD player, and the standalone amplifier. And when you turn it around, you can see that it doesn't only have audio inputs, but also yellow RCA jacks for composite video input. So video sources could be attached to this device, but this is not an AV receiver because it doesn't have a receiver inside. And after removing a couple of screws, we can open the enclosure and take a first look inside. And what we see right away is a large mains transformer and also a rather large aluminium heatsink. And these are two of the most important and also most expensive components that you can find in any classic lab power supply. And that black plastic box that is attached to the heatsink is a so-called hybrid integrated circuit, in German Dickschicht-Hybridschaltung, and that is basically the heart of the power amplifier, and in this particular case this circuit is broken. And in the meanwhile I have brought this amplifier from Cologne to my workshop in East Westphalia, and as you can see I have used my compressor and a blowgun to remove all the dust from inside this device. And then I detached the entire front panel. I unscrewed the bolts from the front panel and took out the various boards that are attached to it. The largest of the front panel boards carries some potentiometers that are worth salvaging and could be useful in the future. The volume potentiometer also has a small DC motor attached to it, making it possible to adjust the volume with a remote control. Next I removed the heatsink that will still have to play an important role in this project. I also unscrew the main board and the back panel. I also detach all the parts that are installed on the back panel, including the power cord that we will not reuse in this project because it doesn't have a protective earth connector. Now, typically in grid-powered audio devices, you don't have protective earth because you don't want to couple additional noise into your audio signal. And that is why these amplifiers typically have plastic parts, or at least insulating paint all around. But I will later on add a blank aluminium front panel to this device, and that is why we need protective earth. In the next step, I then remove the entire main board and clean the entire insides of the enclosure. I then temporarily reattach the heatsink, the front and back panels. Next, I then salvage a lot of components from the main board, including these large electrolytic capacitors, these 0.22 ohms power resistors, this relay, the power switch of the device, this integrated bridge rectifier, and a couple of other parts that you can see here. And many of them will be reused for the lab power supply build. Okay, so now with the original amplifier taken apart and most of the parts salvaged, I can actually start to build my lab power supply. But before I will show you the actual footage, let me show you a block diagram and a little animation that will show you what the situation is right now, or has been in the original state of the amplifier, and where I want to go from here. So first of all, we have a large mains transformer with a single primary winding, and it also has a built-in thermo switch or thermo fuse that is somewhat coupled to the transformer itself. So once the primary winding or the transformer as a whole exceeds a certain temperature, that thermo switch will open so that current can no longer flow through the primary winding. And in the original amplifier, before that thermo switch and primary winding, we actually have a relay circuit that switches this transformer on and off. But at least for now, I will add a simple on and off switch and a fuse to that primary side of the transformer in our newly built lab power supply. And on the secondary side, we find 4 individual windings that comprise 2 pairs, and you can recognize that by the fact that they were wound from different gauge wire. Or if you want to express yourself in a more scientific way, wires of different conductive cross-section area. And with these typical Japanese transformers, these windings are soldered together at one point outside of the transformer, and what we get there is virtually a tap. It acts like a center tap, and that center tap, or these center taps, are connected to the chassis ground, in this case literally connected to the enclosure of the amplifier, and they are defined as the chassis ground or general ground for this device. The larger of the 2 windings is then led to a rather large bridge rectifier, and at the output side of that bridge rectifier we find not 1 but 2 large electrolytic capacitors that are supposed to be charged to plus and minus 38 volts. So what we have here is a so-called split or dual or a symmetrical power supply, voltages that are equal in size but reversed in polarity. And that is used in many audio amplifiers. You can also check that by reading the data sheet of the integrated power amplifier that I have shown you earlier in the video. Now, the other 2 windings also comprise a split power supply that in the original application is used for the pre-amplifier stages, and these windings are wound with a much smaller gauge or much smaller cross-section area. And we will not use these other 2 windings in this part of the project or in this video, but we will use it in the next video when I build that linear regulator. Now, what we have to change now is to connect the 2 windings up here in parallel instead of in series, then remove the second electrolytic capacitor, define this point here as chassis ground, and then add that electrolytic capacitor to the other one so that they are switched in parallel. Now, that will provide us with a plus 38 volts rail for twice the current that the older rail was rated for. And here we can then connect a buck converter and a boost converter, and in the next video a linear regulator. And these will provide us with 0 to 38 volts at high efficiency and a rated maximum current of 8 amperes. The boost converter can step up this 38 volts to up to 120 volts, and it is also specified for a maximum output current of 8 amperes. even though I have a hard time believing that. And that also kind of depends on the magnitude of the input voltage. But we will test that in the future. And in the next video, we'll then have a linear regulator that I will build up myself from discrete components. And that will give us 0 to 38 volts at, I guess, 3 amperes. And that will be continuously adjustable and will deliver an output voltage that is much smoother and less noisy than the voltages delivered by the commercial buck and boost converters. And just that you know it, we're not just talking about adjustable voltages, all 3 stages will have adjustable maximum currents as well. Okay, so outside of the transformer, we can see a little PCB that is sitting on a bunch of pins that come out of a plastic part belonging to the bobbin holding the windings, and I desolder and lever off that PCB. Now we can take a look at the pins themselves, around which the ends of all of the windings are wrapped and soldered. And there is one point where the 2 ends of the larger winding meet. And here I first remove the solder, then unwrap one of the ends and solder it to a wire and insulate that with heat shrink. The other end of that other winding stays on that pin and I solder it on again. Then I take a couple of wires, and they better have a large cross-section area, and I connect them to all 4 ends of the 2 larger windings. And for now I connect a temporary power cord to the primary side of the transformer. This entire thing is connected to the isolation transformer that has all kinds of safety features, and that is why I can do that. But later in this video, this will be replaced with a more permanent and more secure solution. With these things being done, the transformer is in principle ready for action. Now I take a piece of Vero board, measure the length of the heatsink, and then cut a piece off of the Vero board so that it fits actually on the heatsink. In the next step, I drill a couple of holes through that board in order to fit it to the sink. And also after taking measurements, I also drill a lot of holes through the heatsink for a bunch of components that will be installed here in the next video. Now the large bridge rectifier is mounted through the heatsink and soldered to the board, and it is then followed by the other components that you have seen in the circuit diagram, being the 2 large electrolytic capacitors. And here we can take our first measurement of the output voltage, and it is around 38 volts DC. Okay, so what we have here now is a primitive, unregulated DC voltage source that delivers a DC voltage that is superimposed with a 100 Hz ripple. And in order to get rid of that ripple, we need a regulated converter. And as I said before, I'm working on my own buck converters in another project, and I'm also building that linear regulator that we will see soon. But for this project, I actually wanted to try to combine these salvaged parts with a relatively cheap commercial solution that has been around for only a short time. And that are these programmable buck and boost converters that you can find, for example, on Amazon. And I ordered 3 of them, and I will use 2 of them in this project. The first one is this buck converter here, and the second one is this boost converter. Now, before really installing them inside the enclosure, let us have a quick test with an ordinary light bulb as a dummy load. And here I have connected the buck converter, and I'm stepping down the output voltage gradually. And here you can see that you can also read out the current that is flowing right now. And yeah, this is a little control module with LED segments and little buttons. And that control PCB is actually sitting on 2 slots on the actual converter. So it is possible to separate the control electronics and the actual power electronics, and we will utilize that later on in this video. And here you can see the boost converter in action, and this time I'm stepping up the voltage gradually. And you can again see that 7 segment displays and buttons are arranged on a little board that is sitting on 2 slots on the board that carries the power electronics. And we will later use wires instead of the direct connection between the pins and the slots in order to arrange the controls on the front panel and have the power electronics somewhere inside the enclosure. Okay, so the next part of the video will be about how I personally fitted all the parts inside the enclosure, and even if someone at home were to try something similar, I guess the situation would always be a little different because you would have another amplifier, maybe other converters and other tools. So I'll try to wrap this up a little bit. Now, what I did next is to take the original front panel, that in this case is made from plastic and not from aluminium, and I tried to cut out practically the middle section of the entire front panel with my jigsaw, which kind of worked. The problem is that the plastic is basically fusing itself together again after you have cut it. So it took a little bit work with the knife, a little wiggling here and there to get the piece out of the frame that I had created. And after that I drilled a couple of holes into that frame. I cut out a piece of aluminium sheet, also drilled holes in that thing, and then I bolted that aluminium plate onto that frame. In the next few steps, an aluminium angle plate was first cut to length and holes were drilled through it. It was then bolted to the power section of the boost converter. Additional holes were drilled through the heatsink of the buck converter in order to fasten it to the bottom sheet of the enclosure. But before that could be done, some solder joints had to be resoldered because the filter choke and two large electrolytic capacitors were so badly soldered to the PCB that they had completely lost contact. In order to fit the two small control PCBs of the two converters to the front panel, first holes were drilled to the front panel, then a side cutter was used to cut the space between the holes. Then an ordinary file was used to shape those holes into a rectangular form. A very primitive and cumbersome way of doing it. But in this way, at least anybody could do it, even with only the most primitive tools. After that, the two little PCBs were fastened to the front panel with some adhesive. It was MS polymer. And the entire thing had to dry for 2 days in a warm room before I could go on with my work. But in the meanwhile, the power sections of the two converters were finally bolted to the enclosure. Then this type of wire here was used in order to connect the control with the power sections of the converters. And the little plugs on these wires were glued with some more MS polymer to the boards in order for them not to shake themselves loose that easily. And in the next steps, a small board holding 3 power switches was made. One switch for the primary side, turning on and off the entire device, and then one switch for the boost and one for the buck converter. After that, 2 potentiometers, one for voltage, one for current adjustment for the linear regulator, were also added to the front panel. And then 6 mounting posts of different quality were connected to the front panel as well. And 2 of them, the ones in the middle, are also for the linear regulator that we will see in the next video. And I had intentionally left out some space right in the middle of the front panel for 2 old-fashioned meters that will also be used in conjunction with the linear regulator. But, well, for the test at the end of this video, I have actually connected one of the meters, the right one, with the output of the buck converter. So of course we will talk more about the meters, the potentiometers and the mounting posts and these kind of things in the next video when they will actually be connected. After that, the back panel was reconnected to the enclosure, and this time a permanent solution for the power cord was found in form of this jack here. Protective earth was both connected to the enclosure as well as to the aluminium front panel. And in the final step, all things were connected together, also the little control PCBs of the buck and boost converters, of course. And after putting the enclosure back together, we can now have a first test. And I again connect an ordinary light bulb to the boost and then to the buck converter. And both converters work just normally, just as in the first test we had a couple of minutes ago. And I will now show you another test where the buck converter is powering the field winding of a washing machine motor, while the rotor of the motor is actually powered by the boost converter. And you will see some changes in the behavior of the motor as we go along. And one more thing that I want to say here, this power supply, at least in this form, is not powerful enough to really power the motor at its peak power, but it's good enough for a first test. Okay, so this was really just a spontaneous test. I had the washing machine motor lying around and I hooked it up. But already a spontaneous setup like this can teach you something. For example, weaken the current through the field winding of a separately excited DC motor and the motor will spin faster. And well, the next 3 videos probably will just be about power supplies. We'll talk about that linear regulator and about those self-made buck converters. That means a lot of discussion on the circuit level, and especially once that second more powerful and more capable power supply is finished, I'm quite positive that it will help me in developing that universal motor controller that I've been talking about in the past. So just that you know it, I want to focus more again on power electronics. That means switching converters, electric motors, magnetic components and magnetism as a phenomenon. So I hope that you guys like this little project, and even to those of you who are big fans of Sony audio equipment, I hope that you don't hate me for this forever, and I hope to see you soon.